Today we're starting a PowerPoint lecture on factoring polynomials. This is still part of Chapter 4, very important information. And first of all, to let you know, it is part of the California State Standard number 4. We need to know special formulas for factoring the difference of squares, perfect square trinomials, and the sum and difference of two perfect cubes. All the other factoring that we're going to be doing in part of this lecture is included actually in some of the Algebra 1 standards. But we're going to remind you of how to factor those as well. So factor. When you see the word factor in a problem, the first thing you need to do is to understand that we want you to factor it completely. That is called prime factorization. Prime factorization, where every factor of our answer is a prime number and therefore cannot be factored any further. When we're factoring monomials or numbers, a factor tree, of course, can help us to find prime factors. So when factoring polynomials, there's 5 steps you should follow, and you should follow them in the order that I'm going to give you in this presentation. And this will help you make sure you factored your polynomial into its prime factors. Of course, if your polynomial is not prime factors, you will lose some points if you haven't done prime factorization. And yes, there are a few, but not very many polynomials that cannot be factored at all. Usually, though, students will say this because they give up factoring a polynomial they can't figure out. But yes, there are a few that can't be factored. So here's our steps. First thing is to find the greatest common factor of our polynomial. Second thing is we're going to look for any of the 5 special formulas we're going to present in this lecture. Third, we use something called FOIL method backwards. Now this is unique to me, it's not in textbooks, but it's when you have a trinomial with x squared's coefficient of 1. Our book usually lumps number 3 and 4 into the same process, and that's when there's a coefficient of x squared that's not 1. I find it's easier to break this into 2 separate cases rather than lump them into one, which we call this trial and error when it does not have a coefficient of 1. And then the 5th, when there's 4 or more terms, we call this factoring by grouping. So let's find the greatest common factor to try to get it into its prime factorization. So the first step here in Roman numeral 1 is to find the GCF, or the greatest common factor. Once we found the greatest common factor, we're going to use the distributive property backwards, so to speak, to help us factor out that greatest common factor. And if you want to check to make sure your greatest common factor is factored out correctly, you can always use the distributive property forwards to check your answer. Alright, so let's look at an example. 2x to the 4th minus 4x to the 3rd plus 8x squared. When we get each term into its prime factorization, the first term is already prime factored. 2 times x to the 4th. Second term is a negative, so we'll factor out that as negative 1 times 4 can be considered 2 squared, and our variables are already prime factored, x to the 3rd. 8 is going to be 2 to the 3rd power, and then x squared is already prime factored, x squared. Let's find the greatest common factor. What we're looking for is factors that are common to all 3 lists, and we want the greatest number of times that are common. So as we look at the list, negative 1 is here, but not anywhere else, so we can eliminate that. We have a 2 squared, or a 2 to the 3rd. As we look at that, the greatest number of times that 2 occurs on all 3 lists is just 2 to the 1st power. X is common to all 3 lists. The question is, what's the greatest number of x's that are common? Well, x squared is included in x cubed and x to the 4th. So x squared is the greatest number of x's that are common. Therefore, our greatest common factor, or GCF, is 2x squared. Now we're going to use the distributive property backwards to factor that out. We're going to take each term of our original polynomial divided by the greatest common factor, and that's how we will help us find the remaining factor. So 2x to the 4th divided by 2x squared. 2 divided by 2 is 1. X to the 4th divided by x squared is x squared. Negative 4 divided by 2 is negative 2. X to the 3rd divided by x squared is x to the 1st. And then the last term, 8 divided by 2 is 4. X squared divided by x squared is 1. And that will be the prime factorization. And our answer, the prime factorization to factor 2x to the fourth minus 4x to the third plus 8x squared. That's the greatest common factor, 2x squared, times the trinomial x squared minus 2x plus 4. All right, let's look at another example for greatest common factor. And for the prime factorization, 10 will be 2 times 5. Variables are already prime factored. Negative 15, let's call that negative 1. And then 15 is 3 times 5. And the variables are already in their prime factorization. For the greatest common factor, we're looking for factors that are common. Negative 1 is only in one of the lists, so that doesn't work. 2 only occurs in one of the lists, so that doesn't work. 3 is only in one of the lists, so that's not common to both. 5 is common. The greatest number of 5s they have in common is 1. A is common. The greatest number of a's common is one of those, so a to the first. And then b is common. The greatest number of b's they share in common is b squared. So 5ab squared is the greatest common factor. So we're going to take our original polynomial, divide it by 5a squared to find out what our other factor is. So 10ab to the third divided by 5. 10 divided by 5 is 2. A divided by a is 1. B to the third divided by b squared is b. Negative 15 divided by 5 is negative 3. A squared divided by a is a. B squared divided by b squared is 1. So that's our prime factorization of our original polynomial. So from 10a b to the third minus 15a squared b squared, its prime factorization is the greatest common factor, 5ab squared, distributed to the binomial 2b minus 3a. Well, that brings us to Roman numeral 2, special formulas. There are two that we need to start with. They're both called perfect square trinomials. We saw these going forwards where we took a binomial, squared it, and ended up with a trinomial. Now the second half of the chapter we have to work backwards, start at the trinomial, figure out what we multiplied together to get the factors. Now there's 5 criteria we should look for. 5 things to determine if it's a perfect square trinomial. First, obviously, to be a perfect square trinomial, it must be a trinomial. Second, this last term needs to be a positive number. Third, the first terms need to be perfect squares. Fourth, the last terms need to be perfect squares. And fifth, and most crucial, is if we take the square root of the first term and the square root of the last term, multiply them together, and double it, we need to get the middle terms. And we'll worry about the signs in just a moment. If that's true, then we have perfect square trinomials. We factor it as the square root of the first term, the square root of the last term, and then the sine of the middle terms. And that's how we factor our perfect square trinomials. So let's try an example. Z to the second plus 6z plus 9. Let's check. Yes, it's a trinomial. Yes, the last term is positive. Yes, the first term is a perfect square. And the last term is a perfect square. And if we took the square root of the first term, the square root of the last term, multiplied them together, and doubled it, we would get the middle term. So yes, 3z, the square root of the first and last terms, multiplied and doubled, does give us that middle term. So we factor it then as the square root of the first term, the square root of the last term, and the sine of the middle term. So z squared plus 6z plus 9 factors as z plus 3 quantity squared. Let's look at another example. 4s squared minus 4st plus t squared. It is a trinomial. The last term is positive. The first term is a perfect square. The last term is a perfect square. And let's see, we take the square root of the first one, 2s, square root of the last one, t. If we multiply those together, 2st, and double it, yes, we get the middle term. So therefore, it'll factor as the square root of the first term, the square root of the last term, and the sine of the middle term. So 4s squared minus 4st plus t squared factors as 2s minus t quantity squared, and that is my final factor and prime factorization of my trinomial. We have one more special formula to look at in this lesson. It's called the difference of two perfect squares. We saw earlier in chapter 4 that if you multiply two binomials that are conjugates, you multiply the firsts and the lasts, and the outsides and the insides will drop out. So we need to look at this formula backwards. So there's four things we're going to look for. First of all, we're checking to see that it's a binomial. Secondly, that we're subtracting these two terms. It does not, and I repeat, does not work if it's not subtraction. If it's addition of those two terms, it will not work. Third, first term has to be a perfect square. And fourth, last term has to be a perfect square. And if that's the case, then we start out with a squared minus b squared. We end up factoring it into its conjugates, which is the square root of the first term, and then the square root of the last term. And we use one of each signs. One's addition, one's subtraction. So let's try a numerical example for that. Let's check the criteria. There are two terms, so yes, it's a binomial. Yep, that's a subtraction sign. Yes, the first term is a perfect square, and the last term is a perfect square. So we're going to factor them into their conjugates. So we take the square root of the first term. Square root of 25x squared is 5x. The square root of the last term, 16a squared, is 4a. And we need to have one of each signs. One's plus, one's minus. Which one you put first doesn't matter. And that factors into its conjugates. So the prime factorization of 25x squared minus 16a squared is 5x plus 4a, and its conjugate 5x minus 4a. Let's look at our last example for this segment. And that is, first thing we learned about factoring is to check for a greatest common factor. Yes, it's the difference of two terms, but I don't see perfect squares. So look for the greatest common factor. It appears to me, and hopefully you can see this in your mind's eye rather than having to write it out, that the greatest common factor is 3x. So let's divide out. 3x to the 5th divided by 3x leaves us x to the 4th. And then 48x divided by 3x leaves us a negative 16. Now, just because we have found the greatest common factor does not mean we're finished. As I look inside the parentheses, I see the difference of two numbers, and they look like perfect squares to me. So let's keep going. It's the difference of two perfect squares formulas. So we're going to take this x to the 4th minus 16. The square root of x to the 4th is x squared. The square root of 16 is 4. And we're going to have one of each signs, so they end up with conjugates, x squared minus 4, x squared plus 4. Don't forget that greatest common factor. Don't leave it out. Now, some of you are ready to circle your answer, but I again suggest we look. This looks like the difference of two numbers that are perfect squares. So we need to factor x squared minus 4 further. And that is going to factor as the square root of x squared is x, the square root of 4 is 2, and we need one of each signs so that we can get the conjugates. Now, before you go any further, that is my final answer. Some of you are thinking x squared plus 4 can factor further, and let me assure you it is not. Some of you might tell me that that's x plus 2 quantity squared. Well, let me remind you of the perfect square trinomials we just looked at. If you take a binomial and square it, you get a trinomial. Is x squared plus 4 a trinomial? No. It does not factor any further. We had a formula for the difference. If this was subtraction of two perfect squares, there is no formula for the sum of two perfect squares. Well, all right, it's time to wrap up this portion of our lecture on factoring. We'll get the rest of the special formulas and the FOIL method and trial and error and factoring by grouping in future lessons.